In today's video we will talk about a simple type of neuron which is the perceptron. A perceptron is what we call a single unit of logic inside an artificial neural network, so let's get to it. A perceptron is a fundamental unit of artificial neural networks. It's a simple algorithm designed to model the behavior of a biological neuron, receiving input signals, processing them, and producing an output. The perceptron basically takes in several inputs, referred to as x1, x2, through xn, as shown in the illustration. And it makes a decision and produces a binary output, y. In other words, the perceptron is an algorithm or a set of instructions that determines if something is true or false, 1 or 0, cat or dog. The perceptron only consists of one node, like only a small single neuron among the bigger brain of neurons. Before we dive into how perceptrons work or make decisions, let's consider how we humans make decisions. Our thinking process is merely a response to a stimulus, data, or inputs. We see something, hear something, or smell something, and based on that, we make a decision or develop a thought. Imagine you saw this image. What number is this? Your eyes will send a signal to your brain and then it will interpret it as maybe the number 2. This same image, when giving to someone else, can be interpreted as the number 1. So even though we have the same input, the decision can vary depending on some factors in the thinking process. Mimicking how our brains work, if we expose two different perceptrons to the same input data, they can lead to two totally different outputs. But how does that happen? Let's understand this in more detail. In order to make a decision, the perceptron takes in the input data, as we mentioned, and it multiplies each of the inputs with weights. These weights determine how much impact each of the inputs has on the data as a whole. And then the perceptron compares the weighted sum of the inputs with what we call a bias or threshold, B, and then based on the comparison, it reaches a decision and outputs either a 0 or a 1. And that's it. It's that simple. So we take the weighted sum of the inputs, let's call it Z, and evaluate it to check if the threshold is reached. We do the evaluation through something called the activation function. In case of the perceptron, the function is very simple. The function will output 0 if Z is less than or equal to our threshold, B. And it will output 1 if Z is greater than B. But what is this function? There are many types of activation functions, but we'll talk about a simple one called the step function. In the step function we simply choose a threshold, 0.5, or any suitable number. And if Z is bigger than that number, the function outputs 1. Otherwise it outputs 0. And we can put it in another way, we can say that Z is equal to the weighted sum of the inputs plus the threshold. And then compare Z to 0, if it's bigger than 0, then the output is 1, otherwise the output is 0. Another thing we get to choose is the initial set of weights. Remember we said that we calculate the weighted sum of the inputs, right? We choose the initial weights to use. It could be a set of zeros, quarters, halves, etc. Back to our question. How does two perceptrons reach two different outputs giving the same input? The answer is the weights. Based on the weights we choose, the perceptron will make a decision. Just like the number example we saw earlier. Therefore, the accuracy of our neural network, how accurate the results are, or how close they are to the real answer, depends on how well we can adjust the weights to better represent our input data. Let's take an example to better understand how perceptrons work. Assume you want to use a perceptron to decide whether to go to a coffee shop or not. The data you may need to make that decision can be, how close is the coffee shop to your place? How crowded the coffee shop is? And if it's expensive or not. Some of these factors may be more important to you than others. For example, you may care most about the coffee shop being near your house than the other two factors equally. So to say you'll only go to that cafe if it's near your house and either with good prices or not crowded. So in terms of weights, we can assign the proximity factor a weight of 3 as it's the most influencing factor, the prices a weight of 1. And the crowdedness a weight of 1 as well. And the bias or threshold in that case can be -3. Why -3? Because it assures that if the first factor is true along with one of the other two factors, then the weighted sum will be bigger than the bias and the output will be 1. Or in other words true, meaning you'll end up going to the cafe. So let's test our perceptron. Let's say the cafe is so far from your home, then the proximity input will be 0, but its prices are good, and it's not crowded, so both the price and not crowded inputs will be 1. Next we'll calculate z, which will be 0 times 3, plus 1 times 1, plus 1 times 1, which will be 2. And now adding our bias, the result will be 2 plus -3 which is -1. And now comparing -1 with 0, turns out -1 is less than 0, so the answer is 0, and the perceptron will produce false. Oops. You're not going to the cafe. But what if the cafe is near you, the prices are good, but it's crowded? Will you go? Let's ask our perceptron. Now the inputs will be 1 for proximity, 1 for prices, and 0 for crowdedness. Calculating our z, we have 1 times 3, plus 1 times 1, plus 0 times 1, which is 4. And adding the bias, now we have 4 minus 3 which is 1. And now using our activation function and comparing z to 0, turns out z is greater than 0, so the output will be 1. Which corresponds to true. Hooray, you're going to the cafe. Let's say we want to use a perceptron to recognize cats in images. We can represent each pixel in the image as an input to the perceptron, with a weight that determines its importance. We set the weights and a threshold that determines whether the perceptron outputs a 1 or a 0. If the sum of the inputs multiplied by their weights is greater than the threshold, the perceptron outputs a 1, indicating that it has recognized a cat. We can train the perceptron by adjusting the weights until it produces the correct output for a given input. We can do this for many different images of cats until the perceptron becomes good at recognizing cats. Once the perceptron has been trained, we can use it to recognize cats in new images. The perceptron takes in the pixel values of the new image, applies the weights it has learned, and outputs a 1 if it recognizes a cat. So to sum it up, perceptrons learn by adjusting their weights based on the difference between their predictions and the true output. The learning process involves initializing random weights and biases, computing the output using input data, updating weights and biases based on the error difference between predicted and true output, repeating the process until the error is minimized or a predefined number of iterations is reached. In summary, perceptrons are the fundamental units of artificial neural networks. They process input data using weights, biases, and activation functions to produce an output. By connecting perceptrons in layers, we can create powerful neural networks capable of learning complex patterns and data.